you should already know how to solve an equation like x squared equals 25. But what we would like to learn how to do is to solve an equation like 2 to the x equals 25. Notice the difference in these two equations. In the first equation, the variable is in the base, and there's a constant in the exponent. Whereas in the second equation, the variable is in the exponent, and there's a constant in the base. This second equation is known as an exponential equation. And we'd like to learn how to solve one of these. But before we do that, let's just take a look at an exponential equation in general. So let's look at y equals 2 to the x. We can get a sense of what this equation looks like by building a table of values. So let's look at x equals -2, -1, 0, 1, 2, maybe 3. When x is -2, y is 2 to the -2, which equals 1 over 2 squared, which equals 1/4. When x is -1, y is 2 to the -1, which equals 1 over 2, or 1/2. When x is 0, y equals 2 to the 0, which equals 1. When x is 1, y equals 2 to the 1, which is 2. When x is 2, y equals 2 squared, which is 4. And when x is 3, y equals 2 cubed, which is 8. We can plot these points on a graph to get a visual picture of what this looks like. So we're going to need an x-axis, the x-axis, and a y-axis. Now you could use a graphing utility, such as an online graphing program, or your graphing calculator to do this, but it's not a bad idea to get a little practice graphing these things by hand. Now we can plot these points. When x equals -2, y is 1/4. When x equals -1, y is 1/2. At x equals 0, y is 1. At x equals 1, y is 2. At x equals 2, y is 4. And at x equals 3, y is 8. And then if we try to connect these dots in a nice smooth curve, we get a sense of what this graph is doing. One thing to notice is as we go farther and farther to the left on this graph, the function is getting closer and closer to y equals 0. But it never actually equals y equals 0. And you can test some more points or add more points to your table. For example, -3. If you work that out, you get 1/8. -4, it's 1/16. You'll notice that these fractions are getting smaller and smaller, but they're never actually going to equal 0. Another thing to notice about this graph is that it is growing, and it's growing faster and faster. So as x gets larger, y gets larger, but it's growing faster and faster. And that is one of the key features of an exponential equation, where it's growing exponentially. At this point, you should take a little time to look in your textbook at the example of y equals 1/2 to the x. If you look at that example, you'll see that basically this equation is shrinking instead of growing. Remember, graphs are read left to right. So this is becoming smaller and smaller, but that is happening slower and slower. And again, y equals 0 is a horizontal asymptote of this graph. Remember that y never actually equals 0. Like the irrational number pi, there is another irrational number that we have a special letter for, e. E is approximately equal to 2.718. This number e is the base of the natural exponential function. Y equals a e to the b times t. It turns out that by choosing a and b appropriately, we can create any exponential function we want. For example, y equals 2 to the t. We could create that exponential function using the natural base, but we'd have to choose a and b appropriately, and those choices require a discussion of logarithms. We'll begin by talking about what a logarithm is. Log base b of u equals v. This is equivalent to the statement b raised to the power v equals u. Let's consider an example of a log to see if we can make sense of this. Log base 2 of 8. Now, if we're looking at the equivalence here, log base 2 of 8. Our base of our log is 2, so the base of the exponential function it's equivalent to is also 2. We are taking log base 2 of the number 8, so u is 8. In our exponential equation, that's what our exponential equation is going to equal, 8. And the v that we're looking for is the power that we would raise to 2 to get the number 8. Well, 2 cubed is 8. If we consider the original exponential equation we were trying to solve, 2 to the x equals 25, we could rewrite this as a logarithmic equation. The base of the exponential is 2, so the base of our log is 2. The exponential equation equals 25, so we're taking the log of 25. And the power for our exponential equation is x, and that is what our log will equal. So actually, we found a solution to this exponential equation. X equals log base 2 of 25. Of course, now we would need to know how to find log base 2 of 25. What is that number? It turns out most calculators only handle two bases for logarithms. The common base, which is base 10, and the natural base, which is base e from the natural exponential function. Because these two are used commonly and are the two that are understood by our calculator, we have special ways to write those down. And here they are. If you write log base e of x, the shorthand way to write this is ln, read natural log, of x. So natural log, ln, is a short way to write log base e. If you want to use the common base, base 10, it's the common base because it's the base we use for counting, then we write log without a base. Now you need to be a little careful here. If you see ln of x, that always, under every circumstances, means natural log of x, log base e. If you see log without a base on your calculator and in this textbook and in these videos, we will assume that it's log base 10. But in older textbooks, log without a base, and also in some programming languages, log without a base is actually log base e, so this can cause a little confusion. We're going to take a look at a few properties of logarithms. The first property we're going to look at is the inverse property of logarithms. If I take log base b of b raised to some power a, then what should that equal? Well, if we go back to our definition or equivalence of logs and exponential equations, log base b of u equals v is equivalent to b raised to the v equals u. So let's think about what that tells us. That tells us that we want to take the base b, raise it to the power v, so the answer that we're looking for, and that should give us the stuff in the parentheses. Well, let's see. B, in our original problem, raised to what power is going to give us b raised to the a power? And hopefully you see that the answer is a. b raised to the a equals b raised to the a. Now for this property we just learned, this works for any log of any base, And a can represent something more complicated than just a single term. For example, log base 2 of 2 to the x squared minus 3 is equal to x squared minus 3. Our second inverse property looks at the following. b raised to the log base b of c equals something. This one's a little trickier to see. Let's first just look at log base b of c and think about what that means. Log base b of c equals something. We'll call that v. Now, based on our equivalence between logarithms and exponentials, we know what that v is going to do. This v is the thing that if I take b raised to the v power, I get back u, where u was the stuff in the parentheses. It's this u. So in this example, if I take b raised to this v right here, it should equal c. So going back up to our original equation, b raised to log base b of c. Now remember, log base b of c is some value v such that b raised to that value gives us back c. So b raised to the log base b of c equals c. Now if that one wasn't as obvious to you, that's okay. Take some time, see if you can make sense of it, read the description in the book. In the end, it's really important that you just understand that this property holds. The formula we'll look at is the exponents to multiples formula. And this is really the formula that's going to help us solve most of our exponential equations. What this formula says is that log base b of c raised to the a is equal to a times log base b of c. So what it does is it takes the exponent a and brings it out in front as a multiple. Now, just like in the previous equation, it doesn't matter how complicated the base or the exponent are. For example, log base 5 of 3 to the x squared minus 2 is equal to x squared minus 2, the whole thing, times log base 5 of 3. The textbook has a proof of this formula for those who are interested. Now we can use this tool to solve the equation 2 to the x equals 25 in a way that we can use our calculators to help us with. So, our calculators can handle two types of logarithms, natural logs and common logs. So which should we use? Well, really that's a matter of personal preference. Let's look at using the natural log. So I'm going to take the natural log of both sides of this equation. The reason I'm doing this is I would like to apply the exponents to multiples rule, which allows us to take the exponent and bring it out in front as multiplication. Our exponent is x, I can bring it out in front as multiplication. And see, our original problem with solving this equation was that the variable was trapped in the exponent and we didn't know how to deal with that. So I'm going to use this property, and I have x times the natural log of 2 equals the natural log of 25. Now, all I have is variable times constant equals constant. So I'm going to go ahead and divide both sides by the natural log of 2, and I get x is equal to the natural log of 25 divided by the natural log of 2, which, if I type this into my calculator, I get that x is approximately equal to 4.64. Now I can check my answer. I can take 2 raised to the 4.64, and it should be equal to, or at least approximately equal to 25. Now if I plug in 2 raised to the 4.64, I'll find that this equals, or at least is approximately equal to, 24.93. So I might ask myself, well, why didn't it equal 25? Well, that's because I rounded the value of x. If I wanted to get 25 exactly, I would have to keep x as the natural log of 25 divided by the natural log of 2. Or if I wanted a value closer to 25, I could have kept more accuracy on my x, more than just 2 decimal places. So I chose to use the natural log. Well, I could have used the common log to solve the same equation. I could have taken the common log of both sides of the equation. Then I could have used the same property to bring the x out in front of the common log, because again, that property works for logs of any base. Just like in the previous example, I could have divided both sides by the constant that's multiplied times the x. In this case, it's log of 2. And if I type this into my calculator, I find that it is also approximately equal to 4.64. Which is surprising because the log of 25 does not equal the natural log of 25. And the log of 2 does not equal the natural log of 2. But it turns out that the ratios are equal. Let's look at a more complicated example. Suppose I have 5 times 2 raised to the 3x equals 25. And I would like to solve this for x. So the first thing I want to do is isolate that exponential equation. This is the exponential equation. So I'd like to isolate that. So my first step is to divide both sides by 5. And I've got 2 raised to the 3x equals 5, because 25 divided by 5 is 5. Now I can use either the common log or the natural log. I'll use the natural log, and take that log of both sides of the equation. Again, the purpose of this is to use the property, the exponents to multiples property, that says I can take the exponent and bring it out in front as multiplication. So I'm going to do that. Now I can divide both sides by everything that is multiplied times the x. And if I work this out on my calculator, I find that x is approximately equal to 0.7739766031, or if I wanted to keep a more reasonable number of decimal places, 0.77. I should test this, and the number that has more decimal places is a better test. So what do I have? I have 5 times 2 raised to the 3 times 0.7739766031, which, if I type this into my calculator, is approximately equal to 24.9999997, or 25, which is the answer I expected. In the next video and section in the textbook, we'll be focusing mainly on natural exponential functions. Now, we can use the same technique we just used to solve them. For example, if I had 10e to the 4x equals 25, I could solve it using all the same steps I used previously. I could divide both sides by 10, take the natural log of both sides of the equation, bring the exponent out in front as multiplication, and then divide both sides by everything that is multiplied times our variable x. And that'll work. Turns out there's a shorter way to solve this problem, and that's to use the inverse property of natural logs. Back at this step, we could have used the inverse property of natural logs, because remember, or of logs in general. Because remember that the natural log is log base e. So I have log base e of e raised to a power. The inverse property says it simplifies to that power. So this could have been my next step, and then I could have divided both sides by 4.